this case is given to be 0.5 or 1/2. So this is basically to allow you to do your derivation. So 1/2 is because, and also square here is because we are actually looking at the power response, right? So when we are talking about cutoff frequency of a filter or cutoff frequency of a system, the cutoff here is referring to what the half power point. So therefore, we have to look at the power response. And while here sinc function square is because the array or the power response of the array is basically a sinc function, alright? So here, while with this relation for the sinc function, well, you find that you can actually make your life much easier to derive the bin width, right? So the power gain of the array, well, this is something that we've been talking about. Well, it's given by the ratio of the two sine function. Here, well, in the first sine function in the numerator, we have n psi by 2, but for the denominator, we have psi by 2. Okay, so this is for the first part. So basically, to derive the expression for the bin width. And second part, for the same array in part 1, ask you what should be the number of array elements to achieve a bin width smaller than 5 degrees. So basically, here you are asked to use the expression to obtain the answer. Okay, so the derivation goes this way. Now, the very first statement here, in fact, we have already stated the assumption, alright? So the derivation is meant for a large array. So a large array means what? The number of elements n would have to be relatively large. And only then you'll find that the bin will occupy a small solid angle at the broadside. Right? So the array factor is of course for the broadside array. So therefore, if the array is relatively large, then you should expect that the bin will be relatively sharp. That means the bin width will be relatively small. Alright? So with that, we are then ready to show or to derive the bin width, because with that assumption, the array factor can be reduced to a sinc function, and this is something that we have done for the last tutorial. Alright? So the array factor is now given to be sinc of 1/2 of n cosine phi. Alright? So if you have forgotten, refer to the previous tutorial. Okay, so here, well, to obtain the half power bin width, so we equate array factor square. So in this case, sin is a sinc function. That's why you have sinc square, and argument is of course half n cosine phi. So the power response is now set to 0.5. Right? So this is the power response, and the value is set to 0.5. And the next thing what we have to do is to find the phi value. So if the phi value is known, then well, we will be able to find the bin width. So basically, this is what we have. Your array factor. Now here, well, for simplicity, I did not draw a very, I didn't draw a bin pattern for a large array. Right, so this is basically an array, well, for, in this case, 1, 2, 3, 4, 5 elements. Okay, and the bin width is the 3 dB point. So half power point corresponds to 3 dB point. Right, so if this is the gain of the system, then we are actually looking for these 2 points. So how about the maximum gain of your array? It is in this case corresponding to 90 degrees. Right? So here we are taking the array axis to be the reference axis. So therefore broadside corresponds to 90 degrees. Right? So question here is, what is this width? Now since the array is a symmetrical structure, So therefore, the distance from the broadside for the 3 dB point, either on the left or on the right of the broadside, while the wave should be the same, symmetrical. Alright, so the beam pattern is a symmetrical pattern. So here, if we know the value of delta phi, then obviously we know the beam width. So this is the beam width. Alright, so denoted here as theta. So this is the capital letter of the Greek character theta. Alright, so this is of course 2 times of delta phi. So the question here is, then what is delta phi? Okay, so from the equation here, alright, so we have equate the power response to 0.5. So this is your power response. Right? So next we are supposed to find phi. So this horizontal axis is the variable phi. So I should change it to phi. So this is the phi value. Alright? So when you solve for the phi value for the equation, we will know what is this value, right? So this is the value of phi, the value of phi. So we can either solve for this value or we can solve for this value. Follow? So well, if we know this value or we know that value, minus 90 degree, we know the width. Right? So that's basically we are trying to do here. Okay, so with that, well, we have a simple expression obtained. Now, this is the argument of your sinc function, and the question says, well, the sinc function will equate to 0.5. The argument should be 1.3912 divided by pi. So basically do a substitution. Well, then now we end up with cosine phi given to be this, right? So these are all numerical values. And the n here is of course a constant. So with that, we have cosine phi given to be 0.857 divided by n. So we are trying to find the phi here. Now, to find the cutoff or to find the 3 dB point or the half power point, then well, one way is instead of solving for phi directly, what happens if you were to denote the half wave to be delta phi, then phi here will be either given to be 90 plus delta phi or 90 minus delta phi. See that? Plus is corresponding to this point, minus of course corresponds to the point over here. Alright, so with that, well, you find that you can actually expand the term or use your trigonometry identity, right? So you have cosine angle A plus minus angle B. So you have cosine A, cosine B, minus plus sine A, sine B. Do you still remember that? So that's something that you've learned in the past. So with that, well, you find that because you have a cosine term, you have a 90 degree, so the cosine term will disappear because cosine 90 is 0. So left basically the second half of your trigonometry. Alright, and that end up to be sine delta phi. So we can either solve for this point or that point, it doesn't matter, right? So anyway, we basically just want to find the value of delta phi. So with that, the cosine function, well, can be now written as sine delta phi. And if the beamwidth is relatively small, that would mean delta phi to be small. And if delta phi is small, then sine delta phi will be approximately delta phi. Right? And delta phi is, well, in this case, from from here, you can see that we end up with the expression, or we end up with the value we are looking for, delta phi, given to be 0.8857 divided by n. And since this is delta phi, and we know that the beam width is 2 times of delta phi, so therefore theta, which is the beam width, given to be 2 times of delta phi. So delta phi is given to be this. So 2 multiplied into 0.8857, and that will give you 1.77. Alright? So from here you can see that n will basically determine if your inter-element spacing is half wavelength, is fixed. Then n will basically determine the aperture of your linear array. So the larger the n, which means that the more the number of elements, then the larger the aperture, then the smaller the beam width. So n appear in the denominator, right? So does it make sense? Also in this case, it makes logical sense, right? So that gives you the beam width of the linear array. Okay, now the second part of the question asks you, well, if we would like to have a linear array to give you a beam width to be less than 5 degrees, then how many sensors should you use, or how many antennas you should use to obtain a linear array with a beam width of less than 5 degrees? So the expression has been derived, and that is 1.77 divided by n. So it has to be less than 5 degrees. But bear in mind that this expression gives you the beam width in terms of radian, right? So 5 degrees therefore need to be converted into radian. That's why 5 times pi by 180. So with that, while the only unknown is n, do a little bit of mathematical manipulation, well, you end up with n to be greater than 20.3. Okay, now though here you have a fractional value, round 21, round down 20, right? And this is of course closer to 20, but n being an integer, and to be able to fulfill this requirement, so therefore we have to round up the value from 20.3 to 21. Okay, so let's give you the answer on the number of elements. Okay? Yeah.
This one is like you're deriving the half wavelength.
Yes, half wavelength.
Yeah. So
Yes,
in
correct.
the event Rita is half wavelength or Rita is the tag is supposed to assume it's half.
Or you will be told if you are required to solve problems of this nature. Now in many textbooks or in many technical papers, when formulations are given, usually they don't tell you. If they don't tell you, likely it is half wavelength. And in fact, it is actually not necessarily an array of inter-element spacing of half wavelength. In fact, there is no such requirement. In many applications, well, in fact, we can afford to violate the so-called we can actually violate the special Nyquist sampling theorem. You have all done that before, right? I think you have all done sampling theory, right? At least from the second year, right? So you know that you have to have your sampling frequency to be at least twice of that of the maximum frequency value of whatever components in the signal. So in a way, your sampling interval, in this case, corresponds to your inter-element spacing. Follow? So sampling interval to be smaller means what? Higher sampling rate. Because of this so-called twice frequency value. So that corresponds to this. So if you have your inter-element spacing to be half wavelength, so that actually corresponds to a sampling interval which is half of that of your maximum frequency component. can visualize. But for the case of a linear array, sometimes you can actually afford to allow the interelement spacing to be more than half wavelength. It is still actually okay. The reason is because in some applications, so for example, if you are talking about equal side loop array design, so this is your array beam pattern. You'll find that after obtaining the array beam pattern for interelement spacing of half wavelength, in using exactly the same array coefficients, you can actually stretch the array. Of course, what you do is you reposition all the antenna elements, and you can actually remeasure the array beam pattern. You'll find that the beam will become sharper. You follow? Now, and you will not see the side loop, having a grating loop appearing at this direction. The form of violating the Nyquist sampling rate is because once you have the violation, you'll find that after some time when you stretch the array element or the array aperture, after some time you see that you have a very high beam appearing here. And the side lobe may still maintain at a constant height. You follow? So you can see that as long as you don't hit a certain limit, it is possible to still maintain the side lobe without causing the grating lobe to appear. So that is a nice thing about linear array with so-called spatial aliasing being tolerated. So you can actually tolerate to a certain extent the so-called aliasing problem in spatial domain. Now, it is a very specific topic, but it is possible in real application. You can actually violate the sampling theorem to a certain extent. So, though that can be done, but a lot of time we just simply ignore, and we just simply assume that the interelement spacing is always half wavelength, though this assumption is not a necessity. Alright, so okay, any other questions? Now, when you look at the standard textbook, you may not find argument over the so-called aperture design in terms of interelement spacing. What happened that many years ago I have been working on this topic for several years. So that's the observation. So whether an array is a synthesized array or a simple uniform linear array, well, you always have this observation. Now, in case if you are not given the complete information, and if you are not too sure, and if you still need to somehow solve for the solution, well, you can do as what you suggested. Just take the assumption, right? So it is fine. So for this exam, I can accept that. Okay, now question number 2. Here you have a 2-element linear array with a half wavelength interelement spacing. So here you're supposed to steer the loop direction of the array to the 60-degree direction with respect to the array axis using a phase shifter. So you can see only one phase shifter. So what should the phase delay be? Well, so I ask you to write in terms of degree for your phase shifter. So that's the question. Now, the second part here, instead of having a 2-element linear array, well, we have a 3-element linear array. Now, I think it's perhaps better to read the question later on after solving the first part. Alright, so we will just focus on part 1 first. Here, while you are told that you have a 2-element linear array. Now, if you are told that you have a two-element array, but without being told that it is a linear array, can you still solve for the solution? Of course you can, right? So if the array is 2-element, it must be a linear array. You see a straight line formed by 2 points, right? So it must be a linear array. Now, to solve for the solution, I think we have to have this habit, draw the array structure, and that will give you, better insight when you obtain the solution. So you know physically how things happen. So here we have 2 elements, inter-element spacing to be lambda over 2, so half wavelength. So we have with element, and in this case, this is basically a phase shifter, right? But the complex weight has unity amplitude, so we denote it as complex number A. Here, while we have the direction defined with respect to the array axis, so this is the array axis, and the loop direction should be at 60 degrees, so draw an angle 60 degrees. So the arrow here indicates the direction of the source, right? So which means that in radar processing context, you may have a target around here. Alright, so signal being reflected and the wavefront is approaching the array from the direction of 60 degrees. So this is the first wavefront impinging on the array element, and then subsequently after some propagation delay, the wavefront will hit the second element, right, or the subsequent element. So here, wow, you see that the wavefront is approaching the element on the right first, and then subsequently the element on the left. So obviously the signal at this point is leading compared to the signal at that point. Alright? So there is a propagation delay, so therefore the signal here has a phase delay of a certain number of degrees. Okay? So, well, if that's the case, you see that the wavefront at this point may correspond to a certain phase angle. If you take that as a reference, then it will be 0 degree. And then subsequently, while the wavefront will be received by the subsequent element, so the signal will be delayed by a certain amount. So therefore, you have to have this element to actually time delay or phase delay the signal received from this element, so that the two signals, when they are arriving at the summer over here, it will be in phase. So if they are in phase, means what? When you sum them, they will enhance each other. Right? So that is basically what you do when you study interference pattern. If you still remember, if you have done physics before, the double slit experiment, so it's exactly the same concept. Okay, so signals, when they are in phase, they act, and if they are out of phase completely, 180 degree out of phase, then they subtract, or in fact they cancel each other. Okay, so then with the output of the summer, of course, you have the output signal due to your target. Now, to compute the propagation delay or the phase delay, well, we have to know the loop direction, in this case 60 degree. So in your array factor, you have this parameter z, and it's given to be e power j 2 pi f tau. And this is something that we have looked at in our last lecture. Alright, so you can either write this as e power j, k, e power j psi, or you can write in this form, e power j 2 pi f, and then propagation delay. Alright, so you have 2 pi f, f is of course the operating frequency, d cosine phi corresponds to the distance, this distance. And the distance d cosine phi divided by speed of propagation, and that gives you the time taken for the wavefront to travel from one end to the other end. Alright, so this is the propagation delay. So with that, we know that the inter-element spacing d is given to be half lambda, so that's why over here you see with 0.5 lambda. And c here, is speed of propagation, and it is of course given by f lambda. Alright, so here you can see that frequency f can be cancelled out, lambda and lambda can be cancelled out, and that basically left behind e power j pi cosine phi. So in fact, if the inter-element spacing of a linear array is said to be half wavelength, the z parameter for your array factor is always of this form, e to the power of j pi cosine phi. Phi here is the direction of propagation. So it is always of this form. So if the loop direction phi is 60 degree, cosine 60 degree, you have a value of half. So you end up with, in this case, the delay or the phase delay given to be e power j pi by 2, right? So we have a phase shift of 90 degree. Okay? Does it make sense? Now, instead of having a signal coming in from 60 degree direction, if you have a signal from the end fire direction, when the wavefront is traveling this way, first you impinge on the element on the right, then subsequent the element on the left. What would be the phase delay if you have half wavelength? Right? Yes, 180 degree, right? Who say that? Okay, correct. So that would be 180 degree phase shift. As you move up, you see the time delay will be shorter. That means the phase shift will be smaller. And come to this point, when the source is from the broadside, is there a time delay or is there a phase difference? No, right? No phase difference means they are exactly in phase. So that makes sense, right? Okay, so with that, we have the array factor or the general array response to be 1 over 2, 1 plus a z. So this is basically the polynomial of your array factor. So we have 1 over n, the big N. And in this case, 1 is the number of elements, 2. That's why 1 half. And 1 plus a z. So a here is to be determined. You still remember in the previous question that we solved for, we have an an prime. So this is actually the coefficient. Follow? So to allow you to scale your array to be looking at what direction? 60 degree. So here, we have one unknown a, and z is obtained over here. So therefore, you solve for a is e power j minus j pi by 2. And you can see from here, a is basically a phase shifter. What is the amplitude of this complex number? 1. You relate this with the solution. Remember we have shown this a prime psi to be a psi prime. So the question that we just looked at. So we are supposed to solve for the coefficients, and it turned out that the coefficient is basically just a phase shift element. Follow? So what is the physical interpretation? Signal when it is approaching from the 60 degree to loop direction, the subsequent element, the signal received will be 90 degree delay. Alright? So the signal here will be 90 degree ahead of the element on the left. So therefore, you need to delay the signal over here. So how many degree? Of course, minus 90 degree. You follow? So therefore, the overall response for this channel, the phase shift will be 0 degree, and as for the subsequent channel, again 0 degree. You see, the path here give you no phase delay, right? But the physical space give you 90 degree delay or phase shift. So therefore, the element here compensated for the delay over there, and you end up with two signals being in phase when they are summed. Okay, so that gives you the solution for part 1. Now, part 2, here you are given a 3-element, again a linear array with half wavelength inter-element spacing. The reference is still the array axis, and you're supposed to steer the loop direction to 60 degree with respect to array axis, and at the same time set the null direction to 90 degree. For first part, basically you just want the beam to be pointing at 60 degree direction. But for the second part, not only you want the beam to be steered at a particular direction, you are supposed to cancel a signal which is unwanted, right? And where is the signal which is unwanted? It is located at the 90 degree direction. And so here you are asked to draw the beamforming structure and find the array element weighting coefficients. So basically, that's what you have to do. Draw the structure. Right, you have coefficient A1, A2. You have to find what they are. Alright, and then the setting of A1 and A2 should make the loop direction to be pointing at 60 degrees. And at the same time, perhaps if you are able to, write something on your handphone or whatever, there is a one unwanted signal over here. Right, so you're supposed to cancel it, or you are supposed to remove it. How do you remove it? Don't go to the target location and remove it. Removing the unwanted signal means what? Don't let it appear here. You follow? Okay, so you have a signal over there, you have a signal over here. So when you have a signal over here to be received, that is the wanted signal, desired signal. And that's why we will steer your loop direction to look at that signal. Follow? Now, I think this question hopefully will clear a few doubts you have in mind. And if you understand this solution, then basically you have the very basic understanding of the concept of special filtering. So try to pay attention here. So imagine here you have